Other questions?
When you count the group on saturation, when you count the group on saturation, will you always have an even number of H's since we are up, or will there ever be?
You got to account for what the nitrogen or halogen does. I'll go over that probably today. You can have C6H5Cl. Okay, but Cl counts as an H, so it turns it into H6. We'll see that that's on the DUS sheet, and I'll go over that. Question?
I have more of a clarification question. With the IR, you said in your video that we have to be using tables. So on the tests and stuff, do we have the IR table?
No, we'll have tables. You need to know the values.
And I have, with the functional groups, there was on the chart in our workbook or package, it said some of the functional groups have an actual functional group name, but some just has the compound name. So which one would you want?
Whenever it's two, usually either one will work. Like alcohol or hydroxy group, either one will work.
Okay.
Cyano or nitrile, either one will work. Sometimes it only has one. And
And with the carbonyl group, you want us to specify aldehyde or
you could say carbonyl. I say carbonyl. Carbonyl is not a functional group. Carbonyl is a component of many functional groups. Carbonyl will never be an answer to a functional group. It's more specific than that. If you would, whenever you ask questions, please speak loudly so the person in the back corner can hear you, so I don't have to repeat the question. Yeah, go ahead.
In terms of molecular geometry, I know that I'm talking Vesper numbers, like a 2-2 shape versus a 2-1 has a different angle. Can we refer to both those as bent, or no, you want this to be angle as well?
All right. I will never use it.
Oh, okay.
We'll never use that term. But what's 2-2 mean?
Vesper, I mean, like, I'm talking about like a Vesper, like the Vesper, like numbers, like, right, this is a little bit more like
Yeah.
additive molecule.
I don't know what 2-2 means.
Oh, I'm thinking about like, if it has like 2 sigma bonds and 2 lone pairs.
I call that 4 regions.
Okay.
Okay. That's the way I'll do it today when we start doing that. That's 4 regions. And I only will use electronic geometry. Bent is a molecular geometry, right?
Yeah.
I don't discount electrons. I don't see how you can discount electrons. So I don't use bent. Question?
So if it just says geometry, we should always assume that we go down.
For me, yes. And when we start doing examples, we'll see what. Okay, last question, then we'll get started.
Okay, dealing with the IR, is it
Nice and loud, yeah, all right.
is it a safe way to determine the hybridization of the carbon-hydrogen bonds by using the wave number regions? Because you did that a lot in the video, and it's a little bit easier for me to do it by knowing that sp2 would be within a certain region rather than sp3 being below 3,000.
Not quite sure what you mean. Not sure what you mean. Ask me again, or to get more time. You got to be able to look at the structure and tell hybridization. Ask me again. Okay, guys, let's get started. Any questions about the syllabus? Okay, question?
So for labs, do we get any drops, or is it just the average of all of them?
Average of all of them. Any other questions about the syllabus? Okay, we have green sheet for outline. We have the handout I gave you last time. The syllabus also has some pages we may refer to in it, the syllabus packet. And I'll send you an email with two handouts for next week. Do what? If you didn't get it, send me an email and I'll add you to my list. Some of you, I get kickbacks. You have a Georgia Health email or something. If I get any emails, just email me and I'll get you fixed up. Okay, where are we at on the green sheet? ACN, determining total number of bonds from formula, can it be done? In the handout I gave you, there's something like that. It's not required that you know that formula. If it's helpful, use it. Basically, if you're given a big formula, it might be good to know how many bonds are in that formula, ultimately. It's kind of miscellaneous. Basically, problems that are out there, you need to be able to do them, like in the workbook, or ones in the warm-ups. Degrees of unsaturation, we do need to look at that. Hope a number of you have been asking questions. After that, formal charge we covered. Carbon never 5 bonds. Unfortunately, every quiz or test, I'll probably see 5 bond carbons. All right? Don't do that. Carbon doesn't make 5 bonds. It only has 4 orbitals. Resonance, we did a little bit of that. Okay, I know we need to look at DUS and functional groups. So let's see what the handout over here, functional groups and DUS. Okay. Probably let's do DUS first. Okay, DUS you need to be able to do from both formula and structure. Probably let's look at formula first, which is the lower half of this handout. Let's first look at hydrocarbons. What's a hydrocarbon? It's a compound that only contains hydrogen and carbon. CH only. The maximum number of H's that can be in a given compound is 2n plus 2, where n is the number of carbons. Maybe you see something out there that says 2C plus 2. Well, that's where they define N to C, more specifically. 2n plus 2. So if you've got 5 carbons, what's 2n plus 2? 12, because N is 5. Okay? So 5 carbons, the maximum number of H's that it can contain is 12. And if you had thus C, C5H12, you look at it, it's saturated. It's got the maximum it can have. That's what saturated means. Now, let's assume we've already done that. We mentioned that a little bit. But once we look at structure, a DUS is like a double bond, triple bond, or a ring. If this is saturated, it means it doesn't have a double bond or a triple bond or a ring. It has none of those elements of unsaturation. So this can't have that. Now what if we had C5H10? Well, 5 carbons maximum is 12. That's not maximum. How many is it missing from max? 2. Every 2 you're missing, you divide that by 2. 2 divided by 2 is 1. So this is 1 DUS. That's probably what it says there. Every 2 H's you're missing is 1 DUS. Now that's powerful because we know this compound is going to have an element of unsaturation. It's either going to have 1 pi bond or 1 ring. It's got to. If it don't have a pi bond or 1 ring, it ain't going to have the right formula. It won't be C5H10.
Professor,
Yes.
what if you have three short? Do you round up when you divide by 2, round down?
It's going to be an even number. Let's get down here. We'll see some others. Okay, so C5H10 must have 1 double bond and 1 ring. Can't have both because both would be T DUS. The formula only indicates 1 DUS. Okay, what about when heteroatoms are present, meaning non-carbon? It's the same as above, except halogen counts as an H. Nitrogen subtracts an H. Oxygen you ignore. Now this is the way I do it. You may see other ways to do it online or even in the client textbook. Let me show you how I do it. For example, what if you had this big old formula here? How many DUS? Well, What do we do with oxygen? It's ignored. All right, forget, act like it's not there. What do we do with F? Counts as an H. So let's get rid of that and add those 3 to this and turn this into what? 21. And what do we do with an N? It removes an H, so we make this ultimately what?
20.
So this is ultimately C17H20, whenever you do what the others count as. Now that it's C17H20, how many degrees of unsaturation does it have? Well, what's 2N plus 2? 36. So we're missing how many? Divide it by 2, 8. That formula has 8 DUS. That means whatever structure you draw has got to have like maybe 8 pi bonds, or maybe 4 pi bonds and 4 rings, or maybe 8 rings. But that's very powerful. Now we can start having some information to help us draw a structure for this. Now there's other formulas out there, other ways, and actually somebody was just in my office, we were talking about it, their formula says somehow you add a nitrogen. Well, that's because in that formula you were actually adding it to the C, not the H. Okay? There's basically multiple ways to do it. This is the way I do it, and I'm showing you. If you want to do it another way, fine. Just make sure it works for you and you get the same answer. Okay? Now, this is Prozac. If you'll look at the structure, where's Prozac? I think that's in the syllabus handout. Let's see if we see the 8 degrees of unsaturation. Prozac in the, yeah, we did. Here we go. It's got that formula listed on the other page. Okay, 3Fs. Do you see the 8 degrees of unsaturation? How many pi bonds do you see? Well, we haven't quite got to that yet, but this is that's 3 pi bonds, it's 6 pi bonds. Okay, we'll do that today. How many rings? 2. 6 and 2 is 8. There's your 8 degrees of unsaturation. All right. It's a little bit of bookkeeping. It allows you to assess compounds using DUS. All right, question?
Just making sure you always count the ring and the double bonds inside of
Yes.
the ring.
A benzene ring is 4 DUS because it has 1 ring and 3 pi bonds. It's 4 and that's 4. Okay, while we're here, you want to do another one? Real quick. How about Allegra over here? How many DUS?
14.
See, 8, 9. That's another 4 because it's 3 and 1. So what's that? 13. And then double bond there. 14. I think it's 14. Anybody get anything else?
Yeah.
14 DUS. You want to do formula here real quick? We got to learn how to do line bond. What's the formula of Allegra? Lots of carbons. How many carbons? Benzene ring is 6. Okay, quickly you know that. 6 is 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 28, 29, 30, 31, 32. How many H's? You got to know where H's are. Carbon makes 4 bonds. We don't show H's. How many H's here?
One.
All right. 1, 2, 3, 4. There's no H there because we see the 4 bonds to something else. We got 4, 1, 2, 3. There's 5. 5 H's on that ring. Maybe we should draw them in, okay? Don't forget that one. Is there one there? No. There's 5 on this ring. How many here? 2, because for a total of 4 bonds. 2 for a total of 4 bonds. 2. That's a lot.
Isn't there another one? Yeah, there's one.
Where did we miss? Oh, yeah, thank you. There's one there, yeah? Yeah, there is one there. Don't forget that one. None there. Do you see why we don't draw H's in? Yeah. Oh, yeah. I keep missing that tertiary carbon. Not there, not there. Hold on, what is this here? That's a carbon on the end. There's actually 3 there. None there. You see why we don't draw H's? How many there? 38? We'll see if that's right when we do DUS. Okay, how many, what else is here? NO4. NO4? Okay, how many DUS? What do we do with oxygen? Ignore it. What do we do with N? This is not right, because that's going to make it odd. Is there only one N in this compound?
There's an N in the middle, is there? Yeah, but there's just one.
I don't think 38's right. Did we count 37? 37? See, that should be odd, because when we account for the N, it should go to even, then when we divide, we get a number.
Well,
It's 37.
We got 10, 11, 12, 14, 16, 18, 20, 22, 24, 26, 27, 29, 31.
I got 39.
37.
Okay, I think it's 39.
Which one did you force?
That's a good question, because we could use DUS to get the H's right. I can probably count them easier now. Too cluttered up there. If it's 39, what does N do? Turns out to 38. What's 2N plus 2?
66.
How many are we missing?
28.
Okay, we're missing 28. Divide that by 2. What do we get?
14.
Just like we saw from structure. So I confirm it is probably 39 H's. Okay? You can do it from structure or formula. That's DUS. You can read up above. At this point, up above should be pretty self-explanatory. It's just simple examples up there. Question?
So for the future, instead of like drawing out all the hydrogens, can we just use the DUS and find out the number of hydrogens or?
Whatever works for you. Okay. You need to be able to know where H's are. I don't know why we kept missing one or something, but they're all there. I was probably just trying to go too fast there. Question?
In the formula, N is equal to the number of carbons.
It's on the back page. There's another formula there at the bottom. It says 6N plus 2, something, something. That's just another crazy formula for doing DUS. You can check it out. If you like that, use it. There's a half dozen ways to determine DUS, whatever works for you. Question?
So regarding your method of doing DUS, you said ignore oxygen. So like other stuff like sulfur you can ignore too?
Sulfur you can ignore. The reason you can ignore it because it'll just slip in and not change anything. Because it, well. Okay, that's DUS. Let's look at functional groups. Functional group handout. This table here, packet. First are your hydrocarbons, just hydrogen and carbon. Alkane is just going to be a plain saturated hydrocarbon. That's saturated, right? You see the formula? If we drew that out, we would get something like that. 1, 2, 3, 4, 5. There's 4 hydrogens there. Okay? It's all just plain saturated sp3 called alkane. Alkene means it's got the ene in it, and alkene. Alkene is a double bond, carbon-carbon double bond. And so we could get something like this, 1, 2, 3, 4, 5. So it's C5. How many H's here? I see 1 DUS. What does a DUS do to H? H10. You add them up, it'll be 10. Because I see that DUS there. That's an alkene. The double bond can be anywhere. We'll get to that. And then alkynes would be something like this. 1, 2, 3, 4, 5. I like to put an H on the end of my alkynes. It looks kind of negative without it. This is C5, H what? How many DUS do you see?
2.
2. So this is, yeah, see, it's missing 4 H's. Because if you want to make this saturated and get rid of that, well, right now this has 2 H's and 1 there. If you get rid of the double bond, well, now the carbons have to bond to something. You'd have to add another H here and another H here. Then you get to this, 2 more H's. Now it's all saturated. So that's alkene, that's alkyne. I did 5 carbon examples. It could be 18 carbons or whatever. You also have aromatic compounds. This is the granddaddy of all aromatics, called benzene ring. Okay. That's benzene ring, or sometimes called a phenyl group. Lots of different aromatics. When we get to organic 2, we'll see more. You can start having heteroatoms in the ring. If you look at things like your DNA with pyrimidines, purines, a lot of those are aromatics with nitrogen. That's the most common at this level. Lots of the drugs you'll see have like a benzene ring. Now we can get down to compounds that are more than just hydrocarbon. This table calls it CZ bond. I'll basically say we now have a heteroatom. Heteroatom meaning non-carbon. You can have halogens. And you would call that maybe an alkyl halide. Methyl bromide. The halogen can also be bonded to an aromatic ring. That'd be called maybe an aryl halide. Aryl meaning sort of kind of shortened form of aromatic or arene. Halogen can usually all do different halogens. What's an R group? R is typically alkyl. What is alkyl? Alkane. We put a YL ending on it just to sort of make it like a fractal. R is typically just a plain carbon group. Here it's just a methyl. Gotta be careful here. This bromine is bonded to the carbon, not one of the hydrogens, right? A lot of times, write it like that. You know, you could write it like this instead and put the H's on the sort of the outside. A lot of times you just write CH3Br. That really doesn't mean much. It's a halogen. Okay, your alcohols have some type of carbon group with an OH on the end. You know, we did one last time, you know, just like that. Ethanol. We'll learn that 2 carbons is like eth. So that's an alcohol. Here the R group is 2 carbons. In this example is just 1 carbon. You call it the hydroxy group. Don't call it hydroxide. Ide ending means it's an anion. Not an anion, it's hydroxy, or you can put an L on it, hydroxyl. Okay, an ether is where you have an oxygen with R groups on both sides, where that was only one side. It's ether. That would be called dimethyl ether. Diethyl ether is a common solvent. Diethyl ether is used in the Civil War as an anesthetic type. Alcohols and ethers. We get amines. Here we have nitrogen. Now with your nitrogen functional groups, amines and amides, you start putting R groups and it's still an amine. See up here when we added another R group it became a different name. But here it's not. You can have a nitrogen with just one R group, that means it'll have two H's because we know it has to have 3 bonds. Or you can have a nitrogen that has 2 R groups and only 1 H, or you can have a nitrogen that has all 3 R groups as the bonds. Just 1 R group is called primary, 2 secondary, 3 is tertiary. This indicates the number of R groups, or the number of carbons that's bonded to the nitrogen. It's going to be a primary amine. This would be methylamine. Decaying fish has lots of methylamine in it because the proteins break down methylamine kind of smelly. Question?
Like, will we have to specify if it's like a primary amine, secondary, tertiary?
I would know that, yes. The group, amino group, you could just say amine. I mean, this can vary a little bit. Once we go through all these, we'll look at like some drugs and we'll name the functional groups that are in the drugs. Okay, thiol. This is RSH, analogous to ROH. Thiol, sometimes called a mercaptan or mercaptan group. Mercaptan is kind of a slang name for thiol. Basically, both of these are analogous to oxygens. Sulfur is indeed under oxygen in the periodic table. This is called a sulfide. R groups on both sides, analogous to your ether. Sometimes people will call this a thioether. It's like an ether except it's switched to sulfur. And thio is typically slang for sulfur. So thioether. That's very kind of random. Both of these are. I'd probably stick with these names here. Flip side is going to be top part is your functional groups that contain a carbonyl. Carbonyl is your C double bond O, but that's not a precise functional group. Question?
This is regarding the thiol group. Is thiol synonymous with sulfahydryl?
Sulfhydryl?
Sulfahydryl?
Yeah, I think that's another name for thiol. Sulfhydryl or mercaptan. So there's 3 different names right there. You use sulfhydryl in biochem?
I'm familiar with sulfahydryl, so I didn't know if you were okay with that.
Yeah. So carbonyl is not a precise functional group. If you're asked to name functional groups, never say carbonyl. That's a component of many. Your carbonyl, well, the oxygen has its 2 bonds, so there's nothing else going to be there. Carbon needs 2 more things on it. If one of them is R, meaning some type of carbon group, and the other is H, that's an aldehyde. You see, they call all these carbonyl groups. I don't really like that. I mean, precisely, that's called a formyl group. F-O-R-M-I-Y-L, but don't worry about it, it's not here. Aldehyde. Now, if your carbon has R groups on both sides, that's a ketone. Like acetone. Indeed, that right there is acetone. This is a solvent you use in lab, usually to clean glassware. Okay. Also, fingernail polish remover. Acetone, or it could be ethyl acetate. Okay. If we have R group on one side and OH on the other, it's carboxylic acid. This is your most common acid, organic acid. Like acetic acid, that's acetic acid right there. Okay? 5% solution in water, you put it on your salad. Call it vinegar. Okay? Don't put 100% acetic acid on the salad. You won't like that. Carboxy group, that's a good name. Or carboxyl. A lot of times you put an L on the end of these. Okay, if we have R on one side and instead of OH, if we have OR on the other, that means the oxygen has an R group on it called an ester. Esters are super common. Now we can get to another nitrogen. R on one side, nitrogen on the other. These are called amides. Some people say amide. Some people say amides. Some people say amides. I say amide. The long name of an amide, full name, is carboxamide. Now there I say kind of like that, carboxamide. This sort of reinforces that it's got the carbonyl here. Carbon in the oxygen. Because there's other types of amide that you'll see below. The other type of amide, you never shorten it. You say the full name. Now here, if we start putting R groups on the nitrogen, it still remains an amide. See, with the oxygen, you put R groups, it changes the name. Not with the amide. Put one R group on, well, hold on. That right there is a primary because the nitrogen is bonded to one carbon. Here it's bonded to two, so that means this one plus one R group. Here are three, that means this one plus two R groups. Basically, this indicates the number of carbons the nitrogen is bonded to. Question?
So for the carbonyl and the aldehyde and ketone, why don't we just refer to those as like primary and secondary? And why is there a different system in place for it?
The carbon is primary or secondary?
Right.
Usually primary, secondary, tertiary is usually a saturated carbon. It has to be 3 carbon. Usually. That's just not commonly done there. So those are your amides. Last one, acid chloride. A bit random for this introductory table. This is where R group on one side, chlorine on the other. We can add here acyl. These are, we're going to see these more in organic too. It's called acid because these are quickly made from this. And so it's the chloride of the acid chloride. Why only chlorine? Because the acid bromides are just not common at all. These are very reactive. Typically you always see just chlorine there. It's mainly an organic 2 functional group. Okay, there are some I want to add, and then we can see some examples. 2 I want to add. I'm not sure why they didn't let this one off. Nitrile. This is where you have C triple bond N. Okay? C triple bond C is alkyne. C triple bond N, nitrile. Now the carbon is going to have like an R group. Now if that was H, it would be HCN. I reckon that's a nitrile too. Typically they have an R group. Now the actual group itself is called a cyano group. If you were asked to name that, either would work for me. They're both kind of common. It's analogous to an alcohol having a hydroxy group. Okay. The other one is, I can understand why it's not there. I want you to know it because it's in a lot of drugs. Okay? Sulfonamide, another amide, type of amide. But this one has the sulfone part. Sulfone is the SO2. So the nitrogen's bonded to an SO2, the sulfur double bonds to each oxygen, and then an R. You can have primary, secondary, tertiary, depending on how many things are bonded to the nitrogen, just like these amides up there. You would never shorten this to an amide, because if you said amide, you're referring to that one. So this is called a sulfonamide. You may have heard of the, like the sulfonamide antibacterial drugs. And that, they actually shorten that to what? Sulfa drugs? Haven't you heard of sulfa drugs? If you go back to the history of World War II, the soldiers carried sulfa drug in their backpacks. It's the first synthetic antibacterial and saved a lot of lives. And sprinkled it on their wounds. There's also a lot of sulfonamides in like your diabetic drugs. Two others to know. Basically sulfonamide, it didn't have another name. Okay, this also shows some examples. There's a couple more down below. So atenolol, treating high blood pressure. They're already named here. This drug consists of an amide. What type of amide in terms of primary, secondary? Primary amide, kind of the aromatic ring, benzene ring. See this ether? What's an ether? It's an oxygen bonded to two carbons, carbon on both sides. There's an ether. An alcohol, or we could say a hydroxy group or hydroxyl group. Don't say hydroxides. And what is that? Well, obviously it's an amine, right? What type of an amine? Secondary amine. Okay. So now we can discuss the kind of the architecture of the compound. And then you also have this kind of plain hydrocarbon. That's almost not a functional group. It's so plain. It's just kind of the backbone. A couple other things I wanted to point out. Right here. Dayton pointed out here. When your OH is bonded to a benzene ring, you typically don't call it an alcohol. Kind of is. Typically you call it a phenol. OL. What does the OL ending mean? Like alcohol. OL typically is alcohol. But because it's bonded to a phenyl ring, phenol. Don't miss it. If that's a Y, that's a phenyl. That's different from phenol. Okay? So call that a phenol. Now, when the nitrogen is bonded to an aromatic ring, it's typically called aniline, mentioned earlier. Aniline.
Is that a primary, secondary, and tertiary?
That is a primary aniline there because it's only bonded to one carbon.
Are there primary and secondary?
Yes, you can have a tertiary aniline. I threw up this drug last time. What was it that I... Yeah, my cat took. What functional groups are in this drug? Where'd it go?
Secondary.
Carboxylic acid, secondary.
Carboxylic acid.
What's that up top with the oxygens?
Carboxylic acid.
The carboxylic acid up there. I see two aromatic rings, benzene rings. You know, you got those fluorines on it. You can call it aryl fluoride. Kind of so. What do you want to call the nitrogen?
Aniline?
Yeah, it's a secondary aniline. It's like bonded to two rings. It only has to be bonded to one to be an aniline. You got that alkyl group over there, two carbon plain saturated group. It's kind of this plain alkane group or alkyl group. You know, that's just, how many DUS in that drug? Somebody said it, 9? 4, 4, and 1, yeah. From there you can work formula and stuff. So understanding your functional groups helps you discuss compounds. Part of being an organic chemist. Yeah. So in the warm-ups, it asks you to do functional groups, DUS, that type of stuff. I'm going to move on to kind of the green sheet, hybridization. Before we move on, any questions?
When you have two phenol groups pressed against each other, does that still count as two functional groups, or do they become one functional group?
Fused together.
Yeah, when they're sharing two carbons and one single one.
It's called a naphthalene. It's still aromatic. I mean, there's lots of variations on aromatic. Question?
When you're counting degrees of saturation on that one, it counts as 2 rings, right?
Each ring is a DUS.
Okay. Even if they're together.
Oh,
Oh, wait. He was just like based on his question.
yeah, that would be 2 different rings.
So ring, how is that like a closed structure? Like a triangle, three carbons made up, like, they would count that as a, you know what I'm saying?
Yeah, that's a ring.
So is any enclosed structure of carbon basically?
A ring is just cyclic, everything connected in a circle, but it's not a circle. Yeah, that's a cyclopropane ring. 1 DUS. It'd be C3H6, not C3H8. Actually, lots of drugs have the cyclopropane in them.
In Galvus, is that 1 ring on the fluorines in the structure for Galvus on the sheet? Is that also just?
You're gonna have to look at that a little bit. That's a little bit challenging. She's talking about the drug, get the Galvus. Yeah, a little bit challenging. I try to maybe disconnect things, and if you disconnect one bond and there's no more rings left, that means there's only 1 ring. But I think if you disconnect one bond, you'll be left with rings. Maybe do it by formula first, because I think you can identify all atoms if you get the same way by formula. Okay. Under Roman numeral 3, I make a point. If you're asked to draw if you're given a pretty big formula, like C7H6O2, that's not that big. But instead of just doing it 1 atom at a time, you can just throw up a functional group. So I see it has 2 O's, 2 oxygens. I also see that it has some unsaturation because C7 should be able to take 16. It's only 6. It's 5 degrees of unsaturation in there. Because it has 2 O's, I can just start by throwing up a carboxylic acid. And then from there, you can sort of keep working and building your molecule. Okay? Your functional groups are components you can use to build structures. Again, as opposed to doing it 1 atom at a time. So that's just a recommendation, something to keep in mind. All right, Roman numeral 4, let's look at some hybridization. Closer look at bonding. We'll start with methane. Classic example, basic example of sp3. That's what it shows there, yeah. So CH4, what carbon we're going to call. When we do nomenclature, we'll see that the meth is a 1 carbon prefix, and the ane is a alkane saturated ending. So this is methane. Last time we probably drew this on the board, something like this. Right? We said carbon makes 4 bonds. But we didn't address the hybridization of the geometry here. I mean, this looks like this is a bond angle of 90 degrees, yeah? Like a right angle. Is that really the case? No. What we really have is, well, sp3. Now, to do this, see if I can do something over here, make use of this thing. Remember ground state configuration? All right. Let's forget about 1s. Carbon. 2s. We got there, and then we got 2p. Boom, boom, boom. Valence electrons, how many we got? 4. Okay, this is our valence orbital shell here. Something we know about this from studying it. All 4 bonds here are identical. Sort of makes sense. Look like they should be. All 4 are identical. Well, look over here. How are we going to make 4 identical bonds using this here?
Join them all together.
I mean, we could bring an electron from the H and make it here and here. This looks like a lone pair. It's like an orbital with 2 electrons. There's no lone pair on the carbon. And then what do you want to do here? I mean, you can't make 4 identical orbitals, 4 identical bonds with this ground state configuration. Instead, we know that this atom, and most atoms in organic chemistry, don't bond in the ground state. They bond in a what we call hybridized manner. So this is ground state. I'm going to leave this up here. Usually I draw it and end up maybe erasing it, but instead we're going to go over here. We're going to hybridize. What is hybridize? That's just a fancy word for mix. Okay? Mix or combine. Ultimately, what we're going to show is, I don't want to erase that one. Try to leave that. Ultimately, we're going to come over here. To make 4 identical bonds, we need 4 identical orbitals. So let's show. That's going to work over there. 4 identical orbitals. We're going to call these sp3, 4 sp3 orbitals. Now this over here is energy, right? This is also going to be energy. Put it wherever we want. Just make sure that. But over here they have identical energy. How did we get to this point? Basically, we mixed all these. How many are we mixing? We're mixing 4 orbitals. Kind of like this. Let's put these 4 in a blender. All right. Just blend them up. And now let's dish out 4 identical ones. And there they go. Now they're going to be identical in shape and energy. That's all we did here. That's all the theory is. Now, how many valence electrons does carbon have? 4. Now we can show them in each of these. 4 sp3 hybrid. Why do we call them hybrids? Because it's a mix of P and S. We'll talk more about it. Okay? Why do we call them sp3? Because that's what went in the blender. We don't have any other name to name them. Okay? What went in the blender? 1 S and 3 Ps. How many did we fish out? However many you put in, you fish that many out. We put in 4, we're going to fish out 4. But now they're equal. There.
Physical question here is the total energy of the sp3 4 orbitals the same as the total energy of the 2s and the 2d orbitals?
I think yes. My physical knowledge is not supreme. We'll mention something about energy in terms of relative. We can go ahead and mention it. Well, this kind of builds. Discussion builds. Talk about what they look like. At this point, we have 4 identical ones. Now we can put a valence electron in each. Now we can bring in an H in its electron and start making a bond. And I'll draw it as an H, but remember that's 1 electron from carbon, 1 electron from H, joining up to make a 2 electron covalent bond. Using these, now we got 4 identical bonds. That type of theory or explanation fits the experimental evidence, 4 identical bonds. Okay, energy. Where does the energy of these sit compared to over here? Between. Because it's a mix. Are those closer to P or to S? They're closer to P. Why? Because more P went in. And it's kind of like averaging. It's like if you mix 3 scoops of chocolate and 1 scoop of vanilla, what you dish out is going to taste more like chocolate. Okay? So that they're closer in energy. And as we go to the next model, we'll say, okay, how do these compare? So it sits in between. Okay, how are these 4 spread out around that atom? Well, how are these spread out? This was an S around the atom, and these 3 were spread out how? Well, that's the individual shape, but how are the 3 relative to each other? X, Y, and Z. They're all orthogonal to each other. Okay? Well, how are these? These 4 are spread out in a tetrahedral manner. That is, let's see if we can draw that. Put that carbon here. Before we draw it, I need to say one more thing before we start drawing the orbitals. What do the orbitals look like? Like over here, we showed it before. That's a P, and this is an S. What do the hybrids look like? Let me draw you, not an sp3, but let me draw you an sp. If we combine an S and a P, what would that look like? There's an S with a nucleus. Now if we put a P on top of it, sort of like this, now the S has this constant phase all in it. I'm just going to say plus. It's plus all over. The P has different phase. This is, what side do I want to put in? Doesn't matter. Yeah, I'm going to put plus over here. This is negative in terms of phase. Now what happens is, first off, this combination is all really math. It's higher level math. All right? What I'm doing is kind of very simplistic, showing it. And it's actually called mathematical combination of atomic orbitals, MC A. Okay. So basically, this side is plus, that side is plus. These kind of enforce each other or build on each other. So on that side, we have an increase in the electron density. So the result would be over here, you get some increase, and I'm going to start drawing like this. It's sort of rounded like the S, but it also sort of some elongated like the P. What happens on this side? This portion of the S cancels the minus. It's almost like 2 sound waves. Sound waves can come together and build upon each other and get louder. Or actually sound waves can come together out of phase and they can go silent. Just like waves in the ocean. Right? This side cancels out, so over here, it doesn't completely cancel. You get sort of something like that. Right? And this is going to be called, because we combined an S and a P, what do you want to call this guy? An sp orbital. Now one orbital. This little guy here is called the back lobe. Usually we don't draw that when we start drawing our hybrids, because it just gets in the way. Down the road, though, I'll refer to the back lobe, because that's what takes place during a certain reaction. Question?
So these pluses and minuses, the pluses mean it's more electrons in those areas? Or is it
It's basically the phase, orbital phase. There. And reinforcing on this side and not on that side. So we get a hybrid. I'm not going to try to draw sp3 because we'd have to draw 3 P's up here and it'll get very complicated. What we will do is we will compare this. Let's go ahead and compare. What if I drew you an sp3, which was what we're working with? How will this look differently? Well, right here is important. Think about S character. What's the percent S here? One S and one P.
Half.
Half. So we say that's 50% S in that orbital. What's the percent S here? 25% S. Like 25% vanilla, 75% chocolate. So, more P character here. So is this orbital going to be shorter or longer? Longer. It's going to be longer because the P is longer. It's not going to be as long as a true P, but the more P character, the longer the orbital because it looks more and more like a P. The more, on the other hand, the more S character, the more it's going to get rounded and shorter. Okay? That's what you really need to know is percent S character and then relatively think about it. I'm not going to try to draw you an SP3. Actually, on the last page of the handout, I kind of drew them, and they almost all look the same. You got to know percent S and what that means in terms of length and percent S affects your bond length. The longer the orbital, the longer the bond's going to be. Okay, so that's a little bit of that. Now let's draw them around the carbon. I'm going to do SP3, and I got 4 of them. I'm going to draw one. Let's see if I can do this without erasing too many times. Let's do one here. Now you might say, is that a P? We're drawing SP3s. Now, we can also put one over here. Back load. How are these orbitals spread out around the carbon? Tetrahedral. What does that mean? Well, here's tetrahedral here. Tetrahedral, we'll say this many times, is going to be 2 in the plane, 1 forward, 1 back. It's kind of hard to do this. Orbitals. This ain't gonna look right. We'll clean it up with just line bonds. What's the angles in tetrahedral? Yeah. So I don't want to draw this one like this because that looks like a 90-degree angle. I want to draw the other one more like this, that back lobe. With this angle being what? Yeah. Now those two are in the plane. Straight up here and here. Now the other two get hard when I'm trying to draw this. I will just do it and we can see how it looks. Got one here, back lobe, and then it, not like that. We can do it over here. Instead of drawing an orbital, can I just draw a line? Yeah. Okay? How about just a line? There's your orbital. Okay? There's an orbital. Now the other two, one's going to be coming forward, and to make it forward, we can draw it bolded. This is what we can do. Let me put the line here, okay? And there. But this line, I'm going to draw in bolded. This orbital is really coming out at you a little bit. And there's a fourth one I'm going to draw here. Back lobe somewhere. See, that's why we don't draw it. This one's sort of going away. They're the 4. If I do it with just lines, I can do sort of like this. Oh, this might work. If you want to do it, if you want to add in the orbitals now, let's add them in here. Let's just do this, 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 this. And let's all do the back loop. So these are the 4 sp3 hybrids around the carbon. What are each of them doing? They're bonding to an H. What orbital is the H using? The only one it has. What does it have? 1s. What's the shape of an S? Yeah. See, this here is interacting with the H1s, orbitals interacting, and there's two electrons there, one from the carbon, one from the H, and what do we call this interaction of the two electrons? Covalent bond. And so this one is, there's an H here with one electron from carbon, one from H. Okay? One electron from carbon, one from H. One electron from carbon, one from H. So this ends up being, not like that, it ends up being, when we draw the true structure, carbon with bond to H. What is that? Overlap with what type of orbitals? sp3 overlapping with what? S. Every one of these. That's what that is. There's one here. Then there's also one here, coming forward. And then there, I'm sorry, that's back. Sorry. Forward, and then we'll draw that one back. And there's your methane. And if we have a model of it, it's right here. All right, it's not going to be exact. What did I say about two in the plane, straight up and straight that way? That's the plane right there. If that was the board here, see how those are on the board? This one's coming forward. Bold means coming forward. The other one is not on the board, but it's going behind the board. Okay, so that's your tetrahedral. Importantly, if you look at your bond angles, that's not 90 degrees. That's greater than 90. It's 109.5. Why does it prefer 109.5? Electrons can be further apart that way. If we go 3D. Okay. You can also, that's just nature. If I brought in 4 balloons that were sort of a little elongated, it really doesn't matter. If I brought in 4 balloons and tied them all together at the end where it's tied off, guess how they would arrange themselves? That's what you do. All right. That's just nature. See where we're at. Do we have anything up over there? No. There's other things to discuss here, perhaps. We'll move on to SP2 and fill in the holes as we go along. The main thing here is 4 regions. We needed 4 regions. Next example, we'll look at ethene. We're going to have 2 carbons here. Now we have an alkene. Both carbons are identical in terms of bonding. Let's start by asking this. How many electron regions around this carbon? 3. Single bond, double bond region. 3 regions. 3 regions is going to be sp2. Now sp2 means, what did we put in the blender? 1s and how many p's? 2. Only 2 p's. So we're only going to put these 3 in the blender. We need 3 regions, so we're going to hybridize 3 orbitals. Mix these up, what do we get? We put in 3, we're going to get out 3. and they're going to be equal. So there we go. What do you want to call these? Yeah, 3 sp2 hybrids. What's left over? What did we not blend? P left over. Don't forget about what is not hybridized, what is not mixed or done anything. There we go. Energy. Okay. Where do these sit? Somewhere in between. Where do they sit compared to sp3? Which one is lower in energy, sp2 or sp3?
SP2.
That's lower in energy. Why?
It has less weight.
More S character. This is 33% S. That's only 25% S. More S character. They're going to be more like S, thus lower. What about in terms of length? Are these going to be longer or shorter than sp3? Shorter. They're going to be shorter because they're more like S, which is your shorter roundedness. I'm not going to try to draw them. Just know the relative differences. Now, turns out we have 4 valence electrons to this carbon. I'm doing this one, that other one's the same. Turns out we have 1, 2, 3, and it turns out the other one's here. All right? We're not going to pair up there. If we did, that looked like a lone pair. That carbon doesn't have a lone pair. Now we're going to start making bonds. By the way, we didn't name, what type of bond did we make before that was drawn over here? It's right here. When we did this, what type of bond is this?
Sigma.
Sigma, good. What is a sigma?
Single bond.
No, it's a single bond, but what is it? Head-to-head overlap. Okay? We made sigma bonds over here. Hybrids always make sigma bonds. Sigma bonds. What type of bonds do you see here?
Sigma and pi.
Sigma to H. All right. How many sigmas to H?
3.
2. There's a sigma to H's. And then I also have a sigma to carbon. All right. And now we also have a double bond to carbon. Your second bond makes it a double bond. It's going to be a pi bond. Pi bond is used with p orbitals. And all together, what is this? That's your double bond. It consists of a sigma and a pi. We'll draw this.
Dr. Stevens,
Yeah.
is that why you didn't use that other P in the lithium part? Because you had to make that double bond?
That's one way you could say it. There's other reasons. I mean, yeah. We got a pi bond here. It's maybe using the p orbitals. Also, it sort of starts, how many regions around this carbon? How many regions around this carbon? 3 regions. Okay? 3 regions means you meet 3 hybrids. Your hybrids set your regions, your geometry. Okay? 3 electron regions. Let's try to draw this. How are these hybrids spread out? We know 4 hybrids are spread out tetrahedral. How are 3 hybrids spread out? Trigonal, planar. Okay? Your hybrids always hit the geometry that you start quoting. So if we draw that carbon, let's draw 3 hybrids around it trigonal planar. I'm going to draw one this way. I'm going to draw one this way. I'm going to draw one this way. That's supposed to be trigonal planar. I'll do it over here. Line. Boom, boom, boom. Does that look trigonal planar? Yes. This is supposed to be all on the board. None of these bonds are coming forward or back. It's all on the plane of the board. What's this bond angle? 120, all the way around. Okay? Trigonal planar. That's how the 3 hybrids are. What is this hybrid doing? It's interacting with the H. I'm not going to put in the electrons. That's what we had before. Okay? So it's an sp2 to S bond. Aren't each of these sp2s? three sp2 hybrids in a trigonal planar arrangement. It's interacting with an H. What is this one interacting with?
Carbon.
Carbon. And what's the hybridization of that carbon? The exact same. We can draw that carbon over here and do its trigonal planar. Uh-oh. I'm going to make this one a little bit bigger. All right, what's it doing? What do we have here?
Carbon, R, and
sp2 sigma bond. That's head-to-head overlap. Okay, they're coming together head-to-head. Sort of analogous to, here we go, just made a sigma bond right there, head-to-head. All right.
So sigma bonds and pi bonds are both head-to-head?
No, we haven't said anything about pi bond yet. What's left over on this carbon? P orbital. P orbital is perpendicular to this. Now, if this is all on the plane, the P orbital is coming out at you and going back. I can't draw it out at you. I'm going to draw it straight up, and we're going to have to look in the textbook or thing. P orbital, top and bottom lobe, right? This has a P orbital. That's what's left over. Now, what are they doing? Well, first off, there is one electron here, and then the other one is drawn as a carbon up there. But it's one electron making a bond. When you make a bond using p orbitals, these don't interact head-to-head, these interact side-to-side, both above and below the plane, or above and below the sigma bond. So we have sigma bond head-to-head using hybrids. And then what else do we have between the carbons? Pi bond using P's that were left over. That's side-to-side overlap, not head-to-head, but they're side-to-side. Now you may say, well, how do they bond? But you got to remember, ultimately, it's a lot of math and it's electron attraction. We don't get in. Remember that book that thick? Orbitals can interact side-to-side. Guess what? It is a weaker bonding. Pi bond is weaker. As I drew it here, it looks like they're way apart. How do they interact? They're probably actually a little bit closer than what I drew. That's your pi bond. Put your hybrid set to geometry. Your hybrids are in there in trigonal planar. Here, p orbital left over. Questions? Let's do a SP. Let's do the SP. By the way, I do have a model. My model for my pi bonds are not as good. This is the type of model that you would buy. I do have p orbitals in here. Right here, p orbitals. Before I put the p orbitals up there, we had this here. You can see back there. Planar. See how it's planar, flat on the board? Look at that carbon. Can y'all see that? No? See how it's trigonal planar? Boom, boom, boom. Just like that there. Well, kind of needs to go up a little bit. Like that. There's your sigma framework, we can call it. Sigma framework using hybrids. What else is on each carbon? A p orbital. It's perpendicular to that plane, so they're coming out like this. P orbital left over there, p orbital left over here, and they're interacting side to side to make that second bond, the pi bond. Now if I turn it, now I can see I have them both. Now it's like that. You'll see better pictures in your book in color, and they have a plane drawn so you can see the different. I may show those next time, but look in your textbook. Okay. Let's do SP. SP. Oh, important thing with pi bond. Yeah. What do whenever you have a pi bond, you cannot rotate. Sigma bonds can rotate. Example right here. I can rotate them. It's still bonded. Same thing with molecules. You really need another carbon, but that can rotate, stay bonded. This molecule, in which we have a pi bond there, it cannot rotate, because if you do, you will break your pi bond. You'll no longer have side-to-side overlap. For the pi bond, it has to be side-to-side. If your p orbitals are like this, they're not bonded, not interacting. So the important thing there written on the green sheet is pi bond restricts rotation. You'll see some manifestations of that later. Let's do SP. And the compound is going to be called 2 carbons, ethyne. So we have ethyne, SP. Ethyne is an alkyne. It's got the ine ending. 2 carbons here. Both carbons are the same. Let's look at this one. How many electron regions around it? 2. 2 electron regions. Okay? So how many hybrids do we need? 2. So how many do you want to put in the blender? 2. Which ones? S and only 1 P. Let's blend these up. And if we put 2 in, how many are we going to pull out? 2. So there's the 2 hybrids, 2 SP hybrids. What's left over? 2 P's. Okay? Let's do this approach. What type of bonds do you see this carbon making? Single bond is what type of bond?
Sigma.
Sigma, and you see there's a sigma over here. Okay? 2 sigma bonds. We use hybrids to make sigmas. This carbon make a sigma bond to H, sigma bond to H, and sigma bond to carbon. Let's draw this up here. How are these regions going to be spread out? Linear. Yeah. So if you have the carbon, and draw the hybrids, that's a little long. We know SP is really the shortest of the hybrids, right? Because it's got 50% S. So this is actually getting more rounded, but okay. SP has 2 of them. The other one is what? The other one is this, linear. What is this one interacting with? The HS orbital. What is this one interacting with? We got an identical carbon that's also SP. It's interacting with an H. Right here we have a SP-SP sigma bond with a carbons bond. Head-to-head overlap there. What's left over on the carbon? 2 p orbitals on each carbon. 1 p orbital is in the plane. Same thing here. And we can interact those. So there's our second bond, which is a pi bond. But guess what we also have? We have a second p orbital. It is actually coming straight out at you like in the previous example. Hard to draw here. All right? It's sticking out there. Here they are. All right? And half of this is going behind the board. These are interacting this way. I'll attempt to draw it sort of like this. And it's going to get kind of cumbersome and ugly. But you have 2 p orbitals like this interacting. The other 2 are like this interacting. Look in your book for better photos. How many pi bonds did we make? 2. Using p orbitals. Now this graph is just for one carbon. You see that carbon's making two sigmas, one to H, one to carbon. It's also got 2 p orbitals to that carbon. This says your geometry. 2 is going to be spread out linear. We know bond lengths, etc., because this is a shorter orbital than sp3, etc. Let me try to finish this up. Any questions while I'm thinking and looking for...
So just for very simple identifying purposes, a carbon that has just single bonds is going to be an sp3. A carbon that has a double bond is going to be an sp2, and a carbon that has a triple bond is going to be an sp.
Yeah, I think so for carbon.
We're simple just identifying purposes.
2 things we need to do here. First off, let me show you this. We'll be looking at this page on the back next time. Basically, that's my attempt at showing the hybrids. You see how we get more kind of fatter and rounder here? Not a good drawing. 50% S. That's going to make a shorter bond. What about strength? Which one will make a stronger bond? SP also makes stronger bonds because in terms of energy, electrons in this is going to be lower energy than those, right? Because more S character means it's also lower in energy, more like S. And the lower energy your orbitals are, typically they're going to make stronger bonds. All that allows us to understand this table with bond strengths and bond lengths. Okay? For example, why is that shorter and why is that shorter? In terms of bond. Bond strength. You need to understand these trends. Please be looking at those trends and see if you can rationalize it based on percent S character and the orbitals that are used. The other thing we need to do is start applying this. For example, where's the syllabus? Let me ask you the hybridization of what's the hybridization of that oxygen right there?
sp2.
Okay, that oxygen is sp2. Okay, can you graph it like we graph these? What's the hybridization of that nitrogen right there?
sp2. Oh,
Okay.
sp3.
The nitrogen has a lone pair. What type of orbital is that lone pair in? Top nitrogen of ambion, what type of orbital is it in?
S.
It's in the sp2, but that needs to be easily understood. What type of orbital is this lone pair in?
sp3.
No, that's nitrogen is not sp3 hybridized. We need to talk about that. That's an exception. That's an exception. Basically, you need to be looking on the warm-up page, and in the workbook it asks you to identify hybridization of your heteroatoms. You need to be able to look at heteroatoms. We'll also see some miscellaneous carbons next time. Okay. To sort of show the foundation, beginning of the next period, we will do some applications. Please do problems in the workbook where it says graph the hybridization.
I see tomorrow.
I took 12 over the summer.
As we move on, right now,
Yeah, I was like, it's like a number of things, so like, right, technically, right, that yours got 2 p orbital, right? So is that technically, so like on the board, because right, it's referring to carbon, you see there's like 2 sp2 hybrids, so, I'm sorry, so 2 sp hybrids, is it technically so it's 2, like numerically, of 2 sp hybrids? Because that's technically like a 2p, right? Right, the electron configuration. Right, so like, right, these are the one's electron product. This is like the set, right? Because there's one s, then like, right, 2p, 2s, and then 2p, right?
that 2 meaning a shell or
Yeah.